Okay, there. Okay, welcome everyone to our first science panel of the day. And I really want to welcome Michelle Thaller with us again for, I think, the 5th time. Every single con that we have done, she has been our very welcomed science expert, and especially astronomy, which we're very interested in. As you know, Michelle is with the Goddard Space Flight Center, and she's the assistant director of science communication, which was why I can't imagine they could have picked a better person. Your communication skills are so wonderful, and we all appreciate them very much. So I don't want to go into a lot of detail except to say that we share the state of Wisconsin. I didn't know that until I read your full biography, that you went to Waukesha South High School, and I live in Madison.
Oh, nice.
And went to UW-Madison.
So I'm actually calling to you today from Shorewood, Wisconsin. This is my new home.
wow.
I just moved to Milwaukee.
Oh my God.
Shorewood's a little area inside Milwaukee. So we're not that far away. I can wave to you, and
Yeah.
I'm about a 90-minute drive from Madison. So
I have a friend that lived in Shorewood for many, many years. They finally moved to a condo, but they still live in Milwaukee. So
yep.
Yeah, so very much welcome. And I don't want to spend too much time with that because we want to get right into some questions, and Michelle has some slides for us. So we'll move right forward. First of all, we all want to know what your thoughts are on the latest discoveries and projects that are going on related to space science in 2024. And
Well, it's been a really amazing year. I mean,
yeah.
it continues to be. So, I mean, some of the things that I could show you, I've got some pictures of are new things from the James Webb Space Telescope, because with the James Webb Space Telescope, we are just in pure discovery space. I mean, we've never had a telescope that has this type of power looking at this type of light up in space before. And so literally, I mean, close your eyes and point somewhere on the sky, and if the telescope points there, you're going to see something new. I mean, it is that dramatic that I mean, anywhere you look, you're going to see something you've never seen before. And so I can definitely show you some pictures from James Webb and some of the things that just came out last week and so on. And then, of course, the other thing, and all of this relates. I mean, there's no bit of astronomy and physics and chemistry that doesn't somehow relate to everything else. You know, we just finally got the entirety of the canister from Osiris-Rex open. And I think I might have spoken about Osiris-Rex last year, but Osiris-Rex was our mission to go out and sample an asteroid. The asteroid was about 200 million miles away when we took a sample. And we'll talk a bit about, you know, why we find that so exciting. So, you know, if you want, I could answer a few more questions to begin with, and then show some slides and go back and forth. But yeah, so as far as the you know, the huge discoveries, I mean, there's been so many of them, but things coming out of Webb and things coming out of Osiris-Rex are some of my favorites.
I think those sound wonderful. We had some questions about the Artemis moon mission and what's happening with that. And we had some general questions about the solar eclipse that's going to be happening in early April, and a little bit about the little Mars helicopter that seemed to be
yeah,
fatally damaged this past week or so. So
oh, I mean, we honestly, we were getting punchy with it, because I mean, you know, we expected that thing, but for first of all, we hoped it would work, full stop, right? And and then when it just kept going and going and going and going, and it's been, you know, years now, nobody expected that. So I think in the end we were getting a little bit like, let's see what we can do, you know. So a huge success. And
wonderful.
yeah, and I mean, I have to say, when I heard that they were going to try to build a helicopter to fly on Mars, I mean, the first thing that came to the first thing that came is Mars has almost no atmosphere. You know, the atmospheric pressure on the surface of Mars is about 1% that of the Earth. And so this little helicopter is flying at something like the equivalent of an air pressure of 80,000 feet up in our atmosphere. And so it has to move that much faster. I mean, it has to create that much more lift, because there just isn't that much atmosphere on Mars. And you know, we know what happened. Mars's atmosphere was blown away by the sun, and in fact, we can actually see the sun blowing off tons of the atmosphere every day. We have a probe orbiting Mars right now called MAVEN. And MAVEN orbits an elliptical orbit. It kind of scoops down into Mars's atmosphere and then goes out. And the sun, and this is something you'll have, boy, everything's related. The sun, which is something you'll have a chance to see if you go to the eclipse, the sun has this incredible streaming wind of high energy particles, electrons, protons that are going many, many millions of miles an hour. And, in the case of Mars, these basically just strafe off the atmosphere. And over billions of years, we can actually calculate based on different chemicals. The heavier ones sink down and are a little bit easier to keep as opposed to the light ones. Mars has lost about 90% of its atmosphere. So, it's amazing to think there was enough atmosphere at all for this little thing to work. And yet it worked wonderfully. And do you guys know that there was actually a little piece of the original Wright flyer on this little Ingenuity helicopter? Had you heard that?
I've heard that. I think, yeah.
Yeah.
Was it like a little fabric or something?
Yeah, that's right. A little piece of the original Wright flyer. I love it when they do little Easter eggs like that, but that was actually around. But the thing that this really proved to us, and we're going to use it, we're going to use this sort of same thing in a very different setting, is that right now we're building something called the Dragonfly mission. And the Dragonfly mission is also going to be a powered flight. It's actually an octocopter. So it's going to have sort of almost like a drone. It's going to have that kind of configuration of eight little whirling blades. But it's going to be about the size of a car. And we are sending it out to the moon of Saturn called Titan. And Titan has an atmosphere that's actually slightly thicker than the Earth's atmosphere. And in fact, Titan is the only place that I know of in the solar system where you could actually stay on the surface and not need a pressure suit. You'd need some kind of warming suit because the temperature is about 250 degrees below zero. But you actually would have the same amount of air pressure, a little bit more. And because Titan has lower gravity than the Earth, but also a very thick, dense atmosphere, it's a place where if you, again, if you could keep yourself warm, you could actually, like a la the pictures of Da Vinci, you could strap on like big bat wings and you could actually fly. There's enough atmosphere and it's low gravity. And so, that would be something that if people ever colonize Titan, they can have a lot of fun doing. But Dragonfly is being built right now to send out to Saturn's moon Titan. Titan's one of the places where we have a possible, interesting detection that might have been life on it. We can talk a bit more about that if you'd like, because I wanted to show you some of our latest detections of possible life. So
it all sounds amazing.
Yes. Okay.
Yeah.
All right. Well, yeah, let me start with a few things then. Let me share my screen and bring up my slides here.
And I'll do share. Oh, we've got them.
All right, good.
I beat you to it. I set it up a minute ago.
You did. You beat me to it. Thank you.
Yeah, like I said, I'll try to keep a minimum amount of time on the slides. I did want to show you some things. But this gives you an idea. These are currently all the missions that we're operating on the science side of the house at NASA. And basically what you can think of these as most of the non-human spaceflight missions. And that's what Goddard specializes in, but there's definitely some crossover. Some of our most cool science missions are actually instruments on the space station. And of course, we'll definitely have people, the astronauts doing science as they move out into the solar system and all of that. But this just shows you how many. Don't try to read all of the different acronyms, but they're actually grouped according to what we're studying. So the ones that are studying the sun are around this illustration of the sun. The ones that are more deep space, you see around the galaxy in the upper left. The big thing that we do that people don't understand is that NASA really is responsible for all of the Earth science measurements that go on, both in space and a huge amount of stuff on the ground as well. We are the world's treasure for taking the data that's telling us about climate change and what's going to happen in the future and all of that. So this is my, pride and my, the bane of my existence, because I'm trying to figure out, where all the discoveries are coming from and who all is seeing what. But that's what's going on at NASA. And as I mentioned, this is an illustration of the James Webb Space Telescope. We actually did consider putting cameras on it so people could see it out in space. But the problem is the operating temperature is about 400 degrees below zero. So they'd have to be special cryospheric cameras, and we didn't mess with it. But here's an illustration of what it would look like out in space. And of course, we've now had 2 full years of that. And it is just mind-blowing. I actually like to compare it to the Hubble Space Telescope, which is still up and running and producing amazing data. And one of our goals was to have both those telescopes working at the same time, because that way they could sort of cross-check each other. We could calibrate things, one telescope off another. And they also see in different kinds of light. So it gives you a much broader view of what you're looking at. So this is a Hubble Space Telescope picture of the beautiful pillars of creation, which I think hopefully most of you have seen. This cloud is actually not particularly unusual. We see many, many different sorts of clouds like this, composed of dust and gas. The size of this is impressive because one of the pillars, like if you can see my cursor, over here, this pillar on the left, this one finger of this cloud is actually about 5 light years long. And so that would be about 30 trillion miles. And the distance to the nearest star to us is about 4 light years. So this would actually fill the space between us and the nearest star. And you get a sense about how big a cloud that's forming stars can be. And you know, it's absolutely beautiful invisible light. What I like to do is sort of count the number of stars you can see. All the little pink dots are stars. Some of them are fairly new, associated with star formation in the cloud. And then this is kind of a fun thing. This is another picture of that same cloud, but you can actually see that it's part of a much larger cloud that's forming stars. So the pillars of creation that we know are right here in the middle. And the reason that they look this way, these fingers of clouds, is that there's a cluster of newborn stars that are very, very bright and hot. And they're actually blowing away this cloud, like they're actually like blowing a bubble. And you can see that. You can see there's a beautiful sort of edge of a bubble around this cluster of clouds. And this is what a lot of people don't realize, is that we live in a cosmic environment. And not only does the stars give us light and warmth, but they also throw off winds of high energy particles. And we live in that. And you know, the sun's wind, which actually blows a bubble all the way out to past Pluto, the temperature of that wind is about 5 million degrees. So we're actually surrounded by 5 million degree gas. And but sometimes people don't understand quite how diffuse, I would say how rarefied that gas is, because you know, in that case, when you get out in space, you know, in a cubic foot of air right in front of me here, there are 10 to the 23 air molecules, one with 23 zeros. That's how many molecules are in a cubic foot of air. And when you get out there, you're talking about maybe just a couple dozen molecules per cubic meter. I mean, it's much, much thinner. And so when people say, well, wait a minute, how can we be in 5 million degree gas? It would just burn the earth up. And the analogy I often use, and I actually burnt my finger the other day cooking, is if you put your hand into a hot oven, but you don't touch any metal, you know, the air in there is, say, 400 degrees, whatever you've got your oven turned to, but you don't really get burned unless you touch something, unless there's something that can conduct the heat to you. And that's much the way we find ourselves in space. If you just particle by particle, things are very hot, but it's very, very diffuse, so it doesn't really affect our temperature. But you can see that, you know, what the pillars are is that there's star formation happening at the very tips. And that means that gravity is pulling things together to make new solar systems. It's dense there. The rest of the cloud is more diffuse, and it's being blown away by this wind of particles. And so the pillars of creation are shaped that way, because there's basically little pockets of dense star formation that are shielding the rest of the cloud from the wind. And so that's a beautiful star forming region. So here's the pillars of creation again. Now you know why they're shaped that way. They're actually just holding on against this strafing wind. And there's star formation going on at the tips here. And then here's the image that Webb took of them. And so Webb sees in the infrared, a color we don't see in. This would be an invisible, you know, image. The eye doesn't see this. But of course, infrared is what we usually think of as heat light. And so much of that heat gets through the dust of the cloud. And look at all of the stars we were missing. I mean, they're all there, but they're just shining. The light is getting through in a color of light that we don't see. And you can adjust, you know, Webb sees more than one part of the infrared spectrum. So you can adjust which energies, which temperatures you want to emphasize. And I particularly like this image because this next image of the cloud, we really brought out the dust itself. So this is a real image from Webb. This is not a painting. It looks like a painting, but it's not. The colors are assigned so that, you know, we can make an image that our eyes can see. Pretty much consistent with what the colors in visible light, where the hotter things that glow hot in visible light glow towards the blue end of the spectrum, and things that are cooler are towards the red. And they usually try to conserve that. Areas that are hotter or brighter that might assign more of a blue to. But I just love this beautiful cloud of dust. And you can see there are some hot little glowing knots inside. Like I love this one right here. There's a little new star, like a little warm area that's shielding this little bit of dust. Any dust it can hold on to will eventually become its planets in its solar system. And then going into here, so this is a huge finger of the dust cloud. You can begin to see the glowing areas right inside where the star formation is going. It's, I mean, look at the number of stars, and then these little hot knots you see inside the cloud. You know, that's where there are young stars that have turned on, but they haven't blown the cloud away yet, so they're still burning inside the cloud. And you know, that's amazing to see. And here again, right? So you can see that there are these little streamers that might be left. You know, some little solar system is forming in here at the top here, and it's shielding a little bit of dust against that wind blowing everything away. Yeah, it's just lovely. In a different cloud forming region, we actually were able to look in and see the moment stars are actually turned on. And when I say moment, of course, you know, this may be like, you know, a couple thousand years that lasts. But this is an amazing cloud that's forming all kinds of stars inside. And wherever you see reddish colored material, that is actually material that's being jetted off the poles of the stars. So the stars have magnetic poles, just like the Earth does. The Earth has a north and south pole. So does the sun. And so when stars first begin to burn their nuclear fusion reactions, they're not real stable. There's kind of a terrible two tantrum time, and they throw material off along their poles. And so there's a star forming. You see there's probably a star forming right in here in this dense dust, and there's a jet going this way and a jet going that way. And then back here, you see this sort of red oval structure. That's probably like this star right here that's still inside dust. You see these kind of cones of dust, but the jets are blowing away in both directions. And there's even a little one here. There's a tiny little star here. It's got two jets going in each direction. So this is a little party going on. There are stars of all kinds of different mass, the size of the sun, 50 times the size of the sun, 1/10 the size of the sun. They're all being born, and now we can look inside the clouds and see that. And here's a close-up of one, this young solar system. Again, the star is still embedded in this dense little knot of dust in the middle, but it's jetting off this you know, hydrogen and high energy particles along the poles, and those jets can be light years across. So, you know, just a beautiful picture. And seeing this as an astronomer, you know, I mean, we always kind of knew this is how it worked, but seeing the detail, like I said, this is not a painting. This is an actual picture of that young star. And as I mentioned, any of that dark schmutzy stuff it manages to hang on to will eventually form the solar system and the planets. And that disk is already starting to rotate around the young star. It's just gorgeous.
This is so amazing, Michelle. I just wanted to mention that
Yeah.
I never knew that the gas had this kind of directional pull with the stars around it. It just never occurred to me that, because I just used to think, oh, gas is just out there like being gas, but
Yeah.
it's actually pulled. Oh, wow.
It's being shaped. It's being blown bubbles in. And a lot of times when we see like a new cluster of stars blowing a big bubble, new stars form along the edge of that bubble. Because I mean, one of the things about a cloud is that in order to get these clouds of gas and dust to start collapsing under gravity, and that's all that a star is. You take a big cloud of dust and gas, part of it becomes denser, and gravitationally that begins to bring more stuff together. And these clouds are light years across. So there's a lot of stuff to come falling in. And then eventually the temperature inside that little gravitational knot gets to a couple million degrees, and that ignites a natural nuclear fusion reaction. You take hydrogen, the simplest element in the universe, just basically a proton. And under the gravity and the pressure and the heat, it'll actually fuse and become the next biggest atom called helium. And as a lot of you know, this is the only way the universe has to make atoms. The universe began just with hydrogen and a little bit of helium. And that's not a theory. When we look at galaxies and stars that are so far away, with the James Webb Space Telescope, we're now seeing stars that were existing about 300 million years after the Big Bang. So we're talking 13.5 billion years ago. They don't have the heavy elements that we have today. Everything that makes us up is not there yet. And the only thing that naturally fuses, one atom into another is the interior of a star. Every single atom has to be built that way. And we have better and better observations of that now. So this is actually the other side of a star's lifetime from Webb. This is a star that has gone through its life, made many different atoms inside its core, and then finally ran out of nuclear fuel. It blew up. And what we call a supernova explosion. And this is the remnants of a supernova explosion. This cloud is about 12 light years across. Think about this. This was a star, right? Stars are only about, say, 1,000,000 miles across. And this thing blew up. It blew up about 1,000 years ago. We have records from the Chinese astronomers about this one. And the outside shells are still moving at millions of miles an hour out, 1,000 years ago. And inside, we have this beautiful new created material, the dust that eventually becomes us. And it was about a month ago, we had a Webb image of another famous supernova remnant, a cloud that was created when a star blew up. And this one turned out to be very different than we'd ever thought. So once again, this is an expanding shell of material when a star died and violently blew up. And it's about the order of 12 light years across, still moving outwards, millions of miles an hour. But there's so much detail in sort of the shards, the remnants of the star itself. We expected everything to just be gas, kind of amorphous, no big shape. But as we started looking at this, there were all of these weird shards and shapes, and they actually seem to be made of different chemicals. So we can say, like, I'm not sure exactly, but we can say, okay, this area over here, that's making some calcium, and over here that's making some iron, and we can actually pick out bit by bit where different elements are actually forming if we were formed by the explosion in this cloud. And I know you guys know this, but I still think it's something we should teach in the schools. I think everybody should be familiar with this, that the universe has no other way to make atoms, like, iron and sulfur and carbon and oxygen and any of that, other than the only place natural nuclear reactions put bigger atoms together is inside the heart of a star. And I just love that, and I love the fact that we're seeing now a much more detailed look. We have no idea what's going on here. All of this shape that's in this part of the cloud, we're lost. We've never seen anything like that. So we've never had the eyes powerful enough to see that amount of detail. And so it's just wonderful to see all of this shards of new material coming off this explosion. So when it comes to all of the different chemical elements, right? But what makes one element different from another? Why is gold, got HU here, why is that different from lead, and mercury here and all of this? It's really just the number of protons that get stuck together inside the star. That's what one element is. It's different from another, just the number of particles that get fused together. And I love that we produced this here at NASA. So this is our new periodic table. And we now know where, what kinds of stars and what sorts of processes each of our chemicals comes from. And as I said, the only thing the Big Bang gave us was hydrogen and a little bit of helium. That was it.
Wow.
And everything else was formed inside stars. The only other example, when you see a little blue test tube, I guess it's a little blue flask, you can read the code. That one's only made in laboratories. We've never observed that in nature. These are things we make in our particle accelerators, where we slam atoms together and they stick for like 1/1,000,000 of a second, then they decay. And we say, oh, look, that was an element. But I just love the fact that we know which stars it came from which processes, and I think that's just a wonderful thing. I just love this connection. So we're seeing this connection much more obviously than ever before. This is a Hubble picture. This is a visible light Hubble picture of a spiral galaxy. And a galaxy I just love this picture because they're not as flat as you think. They have warps, and there's different ways the stars orbit around. But you know, these are families of hundreds of billions of stars, you know, ours being the Milky Way. And you see all of that dark dust. That's all debris from exploded stars. That's the way you get the dust in these dust clouds. And you can just see a galaxy like this is about 100,000 light years across. So, you know, those huge, you know, lanes of dust, those huge dust clouds that you see there, you know, those are thousands of light years across. And I just sort of love the three-dimensionality of this picture. And you can also see the beautiful blue spiral arms of the galaxy. The only reason these areas are blue is because they're areas where stars are forming right now. They're forming in the dust clouds that make up the spiral arms. And you can see that. You can see on the side, there's a dark, you know, spiral arm of dust. And there's all of these little blue dots in it. And those are all young stars, areas of young star formation. The biggest and brightest stars that glow blue only last about 1 million years. And so they actually, all the stars are just orbiting around the center of the galaxy. They orbit in and out of these spiral dust clouds. But the blue ones only last about 1 million years, so they never make it out of their clouds. There's not enough time for them to actually blow away the cloud and move out of the cloud. They just form in the cloud and die in the cloud. They don't live long enough. And so you only see these bright blue stars for the most part, where you see those lanes of dust. They don't live long enough to ever move out. So, you know, even though the sun, you know, the sun is moving around our galaxy at about 500,000 miles an hour. In the lifetime of the Earth, we've had about 20 trips all the way around the galaxy. So, for example, when the dinosaurs were here, we were on the other side of the Milky Way from where we are now.
Oh,
And
wow.
yeah, and so we move around the galaxy. We've been around about 20 times in the life of the sun. And what we're now seeing is sort of, with this infrared telescope, we can really see how connected all the parts of the galaxy are by these big clouds of dust, these corpses of stars. So this is another Hubble picture of a beautiful spiral galaxy. Once again, notice the blue stars tend to be very close to the spiral arms. The red areas are like the areas where clouds are still inside the dust, warming it up. Stars are forming. The stars are actually forming inside the red areas, but they're just warming the cloud up. They haven't even gotten out yet. And now we're looking at these same galaxies. This is the same galaxy with Webb. And with Webb, instead of seeing all those beautiful stars, it's now the dust itself that's glowing, the underlying skeleton of the galaxy. And as the galaxy rotates and the stars go through it, this beautiful web of dust has kicked up all the way around the galaxy. In the middle of this galaxy, we always find big black holes in the infrared that becomes very devoid of dust. And there's all these bright blue stars. And we're now looking at ways that being around a giant black hole might set off star formation. It just basically radiation and the black hole's gravity itself can help actually trigger star formation. So we're studying that. So I just love that. This kind of shows you, I mean, this is what we're looking at, the visible versus the infrared, what Webb can see versus what Hubble can see. This is why we build different telescopes. They don't all see the same thing. Hubble sees this beautiful star-filled galaxy. The underlying infrared image, the heat image, where things warm, you see this incredible network of dust. And we just released a couple of these images this week. Again, this is another heart of a spiral galaxy. And, you know, and we actually now, this one we released this week, where we now have like 19 different ones that we're looking at. But think about this. We go around inside this disk of dust, and we accumulate over 100 tons a day of this stuff. And we have been going around the galaxy 20 times, accumulating, you know, 100 tons a day, thereabouts. And so, you know, all of this stuff are the heavy elements of life, the things that make up our bodies, everything besides hydrogen. And, you know, you have in you now, we can see, I mean, we were going through this cloud. It's not just like one star blew up and our elements formed there. We've accumulated dust from trillions of stars. Trillions of blown up stars seeded the galaxy with this wonderful warm material, this dust. And then we go around and collect it up, and pretty soon you have building blocks of life. And that's sort of what I wanted to say in addition to this. So how do we sample this cloud of dust that we formed out of? The sun's cloud, we don't even know where it is. I mean, we're 5 billion years old. That was enough time to move out of the cloud and go around the galaxy a couple times. So there's no saying. We can't point to any cloud and say that's the one we formed out of. But what we have are meteorites and then the larger bodies, the asteroids, which are ancient parts of the solar system when gravity was bringing all the planets together. First there were little bits of things, they accumulated bigger things. All of a sudden you have planet-sized stuff. But a lot of little things never changed. They just kept going around and weren't built into anything bigger. So a lot of the asteroids are actually samples of what the chemistry of that cloud was like before planets formed. I actually have one in my living room. I actually even have a sample of an asteroid that we can show chemically is older than the sun.
Oh, wow.
So, yeah, it's actually a little sample of but maybe I can go here. I'll go back. I want to take that, then don't look at it.
That's kind of fun. Wow.
Yes. So this is it's a little slab of a meteorite, but what first came was all of this gas, and then it got sort of bigger and bigger grains. And it sort of formed dust bunnies. As there was friction in the cloud, there was sort of electromagnetism to make sort of big dust bunnies. And then eventually there was enough friction in the cloud that we actually think there were little sparks, tiny little lightning bolts just set off like a cloud makes lightning. Things sort of rub against each other, charges build up, and there are little sparks. And when one of those sparks hits some of the dust, it can liquefy it. And it makes something called a chondrite. And that little gray inclusion that you see there, that little gray bubble is a chondrite. So this was what seeded the planets. At first there was nothing but gas. Then there were areas that were a little bit denser because little sparks had made little drops of liquid rock that solidified. And this is a baby planet that never became a planet, but instead stayed inside an asteroid. It didn't get any bigger. And so that's how we started. And our chemistry is exactly what we find in these carbon-rich meteorites. We have found, as you can see, this little group here, we found in every nucleobase of our DNA, not just little amino acids. We've found that the alphabet of our DNA, we found every single one of those in meteorites. We've found every single organic molecule that makes us up. But here's the thing. We've also found about 10 times more that we don't use. We found nucleobases we don't use, organic molecules we don't use. Life took a small subsection and just used a little bit. We don't really know why. But these people at Goddard are the lead scientists on this mission to bring back a sample of an asteroid. And in this case, an asteroid, I mean, we have meteorites. I mean, this is a meteorite that fell to Earth, but they get contaminated. They go burning through the atmosphere. So to get a real pristine chemical sample, we said, well, let's go out to an old carbon-rich asteroid and bring a sample back. And the magazine had them looking like this. We never have dramatic lighting in a lab, of course. I mean, that's just, and then I love it down here because that's actually really what they look like. They're just the most wonderful people in the world, and they are very happy right now. So we sent out a little probe. This is the Osiris-Rex. That is an acronym, the Origin Spectral Interpretation Resource Identification Security Regolith Explorer. We sent that out to an asteroid called Bennu. This was an illustration that was done before we got there because Bennu turned out to be extremely mountainous and rugged. And there was no clear flat space for us to take a sample. After surveying the whole damn thing, we finally found like 4 locations that were about the size of a parking space, seriously. And so we had to actually reprogram this thing to go down between mountains. It's a whole heroic story. And then so I should say we had a little sort of suction device here that hoovered up a bunch of asteroid material, and we actually had to really race because it turns out we were more successful than we thought. This is a little camera on the spacecraft showing us that we'd actually hoovered up so much our little canister didn't close. It actually was jammed open, and little bits of dust were already leaking out. So we immediately put it in a capsule, sealed it up, and sent it back to Earth. And this is actually from the spacecraft out 200 million miles away. And then we shot that off and it landed in the Utah desert. This is the real thing. September 24th this year. So the last September was when we got our sample back. And we opened it up, and it's sure enough, the suction area is full of all of this wonderful sample of us. So this is a sample of what our chemistry was and the material that formed us. We think this sample is probably about at least 4 billion years old, and nothing's touched it out in space for that long.
Like that.
And the reason we do this is because that's us. Really, that's a sample of the cloud that our planets formed out of, that we formed out of. It has exactly our chemistry. It has exactly our water. It matches isotope by isotope. We basically are meteorite material that was allowed to be stable on a warm planet with a medium that it could dissolve in, water. And you leave it sit for 4.5 billion years, and here you are. But that's actually a sample of us. So I mean, it's that dramatic. And I really think that people sometimes don't get how just as how connected we are. As we went around those spiral galaxies full of dust from dead stars, you have atoms in you from trillions of stars probably. And one of the things, of course, we're now asking ourselves is, do the same solar systems out in space around other stars, do they get the same type of organic molecules? Do they get different ones? And this is an artist's conception, because we actually can't get close enough to this planet to see it that well. But with the Webb telescope, we just took some amazing measurements of a planet about 160 light years away. And for a while now, we've been using Webb. Webb is the first telescope where we can actually see what the atmospheres of these planets are made of, how warm they are, is there water vapor, oxygen, carbon dioxide. It's sensitive enough to actually sample the chemistry. I mean, I should say detect the chemistry. It's not going there. But this is an illustration of that planet. And then by taking the light from that planet and putting it into a rainbow, just literally breaking the light up into a rainbow, we can actually identify molecule by molecule what's in the atmosphere. This is an incredible technique called spectroscopy. Some of you may know about it. I could do a whole lecture on it. That's my specialty. But you can take regular light, put it through a prism, break it up into a rainbow. And if you measure very carefully how much light comes out in all the different colors, you can see things like how hot it is, whether things are rotating, the density of the air. Those all have signals in the colors, and also what molecules are there. And so the thing I'm going to show you, but by the way, this is all public. It's all on our website. Don't worry about any of this. I can give you all of this. But we did this for the atmosphere of this planet. We broke it into a rainbow and measured really carefully how much light was coming. And it made a squiggly line. You're going to see a squiggly line. That's the squiggly line. But all it is a rainbow measuring how much light's coming out in which color. But we're now seeing gases that are hard to get without life, including one here that might be impossible. So we're seeing methane, an organic gas, carbon dioxide, there's water vapor. And then this is something that's still controversial. We're going to follow up on this because the detection is kind of noisy. We need a better, cleaner detection. But for the first time, we've seen a molecule called dimethyl sulfide. And we see it possibly, in the signal of the squiggly line. It's over here too. Dimethyl sulfide is only produced by life. And in fact, it's produced specifically by phytoplankton. So we know there's water vapor, and this is an Earth-like planet. It's solid. We know that, and it has lots of signals of possible oceans from the air pressure, from the water pressure, from the water vapor in the atmosphere, and now we have what might be, if it holds up, a detection of a phytoplankton, plankton.
Wow.
My friends at SETI, the Search for Extraterrestrial Intelligence, that are looking for signals from alien civilizations, they're always like, you guys are looking for pond scum. It's like, I'll take alien scum. I mean, as long as we know, for sure. I think with Webb, I mean, I don't think any of us expected it to be this sensitive. It's better than we thought. And I'll kind of leave it there for a little while and take some questions. It's been an amazing ride, and we might be hot on the trail of the first life outside the Earth, the actual scientific detection of it.
Where is that planet, Michelle? That particular one with those dimethyl,
What I could do is I can find the press release and put it in the chat. It's a phone number. right? I mean,
Oh,
there's no name to the
right, no
planet.
problem. Yeah.
Yeah. And there's no name to the star. It's
Oh, okay, so it's
yeah.
not like we can go look it up somewhere.
Oh yeah, well you certainly could. I mean, so it's something that it's a relatively nearby star, 160 light years. I know that's our neighborhood. And I can certainly give you the coordinates and stuff. And I mean it's a dim star, so I don't think you could see it in like a non-professional telescope. I think like I mean something like Mount Palomar can see it, and and the
Right,
really
of course.
sensitive ones. Yeah, but I mean if you want to know what part of the sky it's in and things like that, I can get that data. Yeah.
That's just amazing. So that's how you can tell, like when you're saying about spectrography, how you can actually tell what things are. That's
Yep.
how you can say that this might have life because of that substance. Okay.
Yeah, this particular chemical requires biology to create.
Right.
And
Wow. Okay,
and
that's
so
great.
yeah, so if it holds up, then it's going to be hard to say. I mean, of course, when can you say 100% as opposed to like 99%? And I think this is an argument we'll have at NASA. Well, a discussion. I mean, it's because somebody might come along and say, well, look, okay, so on Earth, we don't know any other way to produce dimethyl sulfate other than life.
Right.
But I mean, how do we know what this planet is like? This planet could be totally different, And I think that there may always be that tiny bit of doubt. But if you have methane, carbon dioxide, water, and oxygen, those are hard to get all at once. None of those in and of itself means that there's life there. We see plenty of worlds. Mars, for example, had high levels of oxygen on it. May not have had life. Carbon dioxide, Venus is full of carbon dioxide. Methane, we see plenty of methane. Yeah, the ice giant planets are made of that stuff. But getting them all four together is hard. And then when you have all four of them together, plus what we call a biomarker molecule, something that we think marks life, I think it's pretty guaranteed. I mean, it may be 99.9%. You may never be able to say completely yes, but I've got a bottle of champagne chilling, and I have for decades because someday we're going to have a real detection of
Right.
life. I mean, a real scientific detection, and I want to be ready to celebrate.
Yeah. So Michelle, how is it that in a small solar system such as ours, at least I think we're small, that one planet would end up with that and the others not? I mean, how did we luck out? Is there something about our planet that?
Yes. Yeah. And there's something that people don't think about much. And unfortunately, it's something we can't detect at a distance yet. And that's our magnetic field. A lot of people, I mean, I go around singing the praises of our magnetic field. The Earth has a wonderful core of molten metal. And there's something also, it has a spin. We're also a fairly fast spinning planet as planets go. And something about the way that molten metal moves around generates a strong magnetic field. So we have our North and South Pole. And what people don't realize, like I said, we live in an environment filled with high energy particles, wind blowing through the solar system. And not just from the sun. There are stars that have very strong magnetic fields. There was one, and again, this is something I can show you the information for. There was one star that had a little anomaly on it, kind of basically the equivalent of a giant solar flare. And this was in 2007. And it actually sent out a burst of strong stellar wind that blew off the top of our atmosphere. We actually detected it with our high energy satellites in 2007. And then from where this blast came from, we looked back to where the star was, and the star was 50,000 light years away. So we live in an environment of winds of particles. And the amazing thing is that these particles are so high energy, they're electrically charged. And what a magnetic field can do is change the path of electrically charged particles. Mm-hmm. So if you're a proton or an electron, which the wind mostly is, that electric charge feels our magnetic field, and it goes around us just like water around a boat. And that's the source of the northern and southern lights, is that some of those high energy particles go down close to our poles, but most of them are just diverted around. And in the case, Venus and Mars, both of them, we now have evidence, used to have Earth-like environments. We think they had oceans, rain. Venus might have been the first world that was habitable, because when the sun was younger, we think it was dimmer. Stars naturally become hotter and brighter over the course of their life. And so, 4 billion years ago, when life was just forming, the Earth might have been too cold, but Venus being a little closer could have been the first one. So there was a time when there were 3 Earth-like planets in our solar system with oceans, snow, rain, possible life. And the problem is that Venus and Mars don't have strong magnetic fields. We don't understand why. In the case of Venus, Venus is much the same composition as the Earth, but Venus rotates very slowly. It takes, it's like 260 days for one day on Venus.
Wow.
And somehow, we're not sure that it's related, but it might be, that it just never got a strong magnetic field. In the case of Mars, Mars is only 1/10 the mass of the Earth. And so we think that the core probably just cooled off and doesn't have a lot of activity anymore. And we in the soil of Mars, we see evidence that there was a magnetic field, because as you dig in, you can see places where all the iron is lined up one way or lined up another way. So it had a magnetic field, but it just went away over time.
Oh my goodness.
So the reason we're alive at all is we had this strong core and a strong magnetic field. And that's something we can't tell for planets, around other stars yet, as to which ones have this. So it's something a lot of us don't think about. And it's also the reason NASA is not, I mean, we would love to have astronauts back on the moon and on Mars. They are not protected by the Earth's magnetic field when they get that far away. The space shuttle is the space station and the space shuttle at the time, they're largely protected. They actually orbit around close enough that they're inside the magnetic field. The astronauts still get more radiation than we do because they're not protected by the air, which absorbs a lot. But the problem with even out by the moon, if the sun had a bad day, and it does routinely, this is not uncommon, where a lot of solar wind comes out, it would have killed the astronauts. And in Apollo, we got lucky. I think it was between Apollo 15 and 16, and that was only like a 6-month period. There was a blast of solar wind that would have killed them all if they were on the moon. And getting people all the way out to Mars, which is a 6-month journey, then you stay a year on Mars for it to line up again. So we can, because Mars is its own planet, so it's going around the sun, sometimes we're on opposite sides of the sun. We'd have to somehow shield them from that for like 2 years. And
would it be water, Michelle? Because I heard talk about water, some kind of like a wall of water, like a bubble where they.
Yep. So water works as great. Water absorbs this stuff very well, but you'd need maybe like a meter or 2 of water, like a 6-foot tank.
Wow.
And right now we're not designing things that are that big. I mean, once you have a place like a colony on Mars or the moon, the other thing is you only need to dig down under the soil about 10 feet and you'd be protected. The soil on Mars, 10 feet of it on the moon or Mars would shield you. But then you need to bring, tunnel diggers and machinery and all of that. So, it turns out actually that one of our interns, Christina Cook, is one of the next astronauts to go on Artemis, and they're going to orbit the moon and then come back. I wish I had better news. I mean, our budgets are getting cut. NASA got a $2 billion cut this year and probably a similar one next year. And we just don't know how to protect people from this radiation unless they give us money to build bigger spacecraft. And
I think you should go talk to Congress, and I think you.
Yeah.
So I mean, I would love to see it. I really would. But I think with the budgets going right now, we're not going to see it anytime soon. We might see another kind of short touch and go Apollo type missions. But I mean, all of us were hoping for like a real sustained presence on the moon, and I don't know if we're going to see that. I wish I could say yes, but I think maybe for a while we just won't have the money.
So the Artemis, what's the status of Artemis at this point?
Well, basically that, it's the rocket they're using, the SLS, has worked really well. It's an odd rocket because it uses old shuttle engines. It uses, I mean, seriously, almost antique engines that were built for the shuttle program but never used. And we only have enough spare shuttle engines to launch that rocket, I think 4 times. And then, of course, we're thinking about things like, we buy a lot of our rockets from SpaceX. We buy, some from Boeing. That's nothing new. We've bought our rockets from, even during the Apollo program, the rockets were provided by contractors. But right now, there's not a real big human-rated lift rocket. We use the Falcons to get up to the space station and back, and those are very good and they're quite reliable. But we don't really have another moon-rated rocket and except this SLS rocket, which we could only build like 5 of. I mean, I don't know. Anyway, the other thing is that the whole Artemis program was meant to be a big encouragement for commercial spaceflight. And SpaceX, for example, has the contract to build the lunar lander. So it's not done yet. You know, I don't even actually know how far along they are. So part of it is, you know, it's complicated. And the way the US government decided to do this was not just NASA, go build yourself a rocket. A lot of people who remember Apollo, I mean, everything changes, I get it. But they remember that when you were at NASA, you know, and Kennedy said, you know, build this now because we're in competition with the Soviets. You know, you just go into the workshop and if you needed a certain, you know, part machine, they'd machine it, you know, and then you'd go build and now it's layers of contractors and layers of private industry as well. And that's going to mean it takes a lot more time. Yeah. So I know at first they were saying that maybe we're going to go in 2024. I don't think they will. And this next one will just be like an Apollo 8. It will go around the moon and back. It won't land. It will take people farther out than Apollo 8 and actually farther out than humans have ever been before. It'll do kind of a long loop around the moon. But yeah, I would love to see people hopping around on the surface of the moon. We need a lot more moon rocks, a lot more samples. The moon rocks they brought back revolutionized our view of the solar system. It's completely changed it. So but I wish I could say that we're going off this year. I don't think so.
Well, on that unhappy note, we do have to close out this session to get ready for the next one in several minutes. So really appreciate you once again. I wish we could listen to you for another 2 or 3 hours. We would all love that, but we appreciate you giving us this time.
Well, thank you.
And I do it again.
And I also want to say one of the things I've really been enjoying recently is talking a lot about the contributions of women in astronomy. Because I think people don't realize, I mean, given the small number of women that were in astronomy 100 years ago, just how central and seminal women's work was to all of this. You know, people who discovered what the stars were made of. Yeah, I mean, it's an amazing story about how the women that were in astrophysics made, I think, the most profound basic discoveries about the universe. I encourage you all to research that too.
Including yourself.
Yes.
Oh, well, yeah.
Yes.
Maybe we'll ask you to do that. In fact, we'll keep that in mind for next time.
Yeah.
It would be great since the protagonist of Vera's books is a young woman who is
Well, thank you so much for having me. It's nice to see all of you again.
Thank you, Michelle. Have a great time yourself and
enjoy.
Have a great eclipse.
Oh, yes. Oh, I should just mention, you definitely want to go see the solar eclipse, and you will see this wind. That's one of the reasons I love solar eclipses. So when the moon is completely covering up the sun, you can look at the sun without any filter. It's safe. You can just look at, and so, but when you look up with your own eyes, you will see this incredible streamer-like effect coming away from the sun. And that's what I'm talking about. Those are winds of high energy particles. It's the only time you can see it with your eye is during an eclipse.
Look for that. Thank you.
Yes. So look for this wind, and remember that we're in an environment, both from stars and the sun, of winds of high energy particles, and that actually limits the life of planets. And luckily, we are protected by our magnetic field. Anyway,
thank you so much, Michelle. Thank you. This was wonderful.
And to everybody who joined us, thanks for joining. And the next session is our Champions Trivia Challenge in just about 7 minutes. So join us for that, whether you want to, just to watch. So thanks. And thanks again, Michelle.
Thank you, Michelle. Next time.
Bye.
Bye-bye.